The equilibrium constant, Kc. Chemistry Explained are chemistry lessons designed for you to participate in. So make sure that you are writing notes and completing tasks on paper or on tablet. Move through the lesson at the pace that suits you. Skip ahead or move back as you wish. Most importantly, when prompted, pause the lesson, complete the task, but taking your time and thinking the problem through. Resume and check and correct your answers before moving on. The topic overview. We start with the equilibrium law and the equilibrium constant Kc, to the units of Kc, then calculating Kc from equilibrium concentrations, and then how Kc values relate to the position of equilibrium. If we consider a general reaction equation in terms of A, B, C and D, we'll see here that we have reactant A, capital A and capital B, with their balancing numbers or coefficients, small a and small b, two products, capital C, capital D, balancing number small c, small d. So those are the four components at equilibrium, at constant temperature. The equilibrium law quite simply states that the concentrations of the right-hand side, that's the concentrations of C and D, raised to the power of their balancing numbers, divided by the concentrations of the left-hand side components, that's capital A, capital B, raised to the power of their balancing numbers or coefficients, equals a constant. Just to remind you, the square bracket is the symbol for concentration in terms of moles per decimeter cubed. That constant is called Kc, the equilibrium constant. So, for any starting concentrations of A, B, C and D, the same value of Kc is obtained at equilibrium. So you start with lots of A, lots of B, no C, no D. You'll end up with a Kc value at equilibrium that is the same as if you start with lots of C and lots of D and no A and B. However, temperature does affect the value of Kc. Hence, we have to specify earlier on that we are at constant temperature. So the value of Kc is maintained for any starting concentrations of ABCD at equilibrium at constant temperature. So here are some problems for you to try. Pause and write equilibrium constant expressions for A, B, C and D here. So we've got iron and thiocyanate giving us iron, thiocyanate, iron. I hope you recognise that from an earlier lesson. Then we've got hydrogen and iodine giving us hydrogen iodide, etc., etc. So pause and write 4 Kc or equilibrium constant expressions. Come back to check your answers. Okay, so let's have a look at the first one. Well, Kc will be the right-hand side concentrations raised to the power of their balancing number. The balancing number is 1. So the concentration of the iron thiocyanate is raised to the power of 1, which we don't write. So we've got Fe3 plus and the thiocyanate ion on the left-hand side. So their concentrations are on the bottom, raised to the power of 1. Let's look at the next example. Kc is concentration of hydrogen iodide squared, because the right-hand side is hydrogen iodide with a balancing number of 2, and the left-hand side, hydrogen and iodine concentrations raised to the power of 1. Now, it may be that you need to pause and try the next two and make sure you get those right before we move on. But I'm going to reveal C. On the right hand side we've got 2 moles of sulfur trioxide, so SO3 concentration raised to the power of 2, and then 2SO2 and O2 on the left hand side, so SO2 raised to the power of 2, concentration of O2 on the bottom. So those are the 3 Kc expressions. And then notice on the last one we've got B and D are simple reversals of each other, and therefore the Kc expression is reversed. The right hand side on this example is hydrogen and iodine concentrations, and on the bottom we have the left hand side, which in this case is hydrogen iodide raised to the power of 2. So you'll see that when you compare B and D, one feature of the equilibrium constant is that you have to have an equilibrium expression to which the constant refers. So you can't say, oh, the equilibrium constant for the hydrogen iodide, hydrogen iodine equilibrium. You have to specify in which direction you are writing it, left to right. So here, hydrogen and iodine appear on the bottom because they are on the left-hand side. If we reverse the way that we've written the equation in example D, then we've got hydrogen iodide on the left-hand side, so that appears on the bottom. And of course, that gives 2 different values for Kc, which of course are 1 over each other, reciprocal values. Strictly, the units of Kc are from year 2 of the OCR A specification, but it does fit very neatly here and is well worth doing at this point. So let's try some examples. I'm going to model the first one for you so you can see how it works. So here's my Kc expression for the iron 3 thiocyanate ion with Fe3 plus ions and the thiocyanate ion. That's from an equilibrium we met in an earlier lesson. So that's the equilibrium constant expression. How do I work out the units? Well, the units of concentration are moles per decimeter cubed. So I've got moles per decimeter cubed on top divided by moles per decimeter cubed times moles per decimeter cubed. So I write that over here. So instead of putting in values for the concentrations, I am putting in the units. Then we can see here that 2 sets of these units cancel out. So I'm left with 1 over moles per dm cubed. So that will translate to bringing it all up on top. So moles to the -1 dm cubed. So there are our units. Now if you're not clear, 1 over moles is written as moles to the -1 on the top line, and 1 over dm to the -3, 1 over dm to the -3, if we bring that to the top, we change the sign so it becomes dm cubed. Okay, so if you've seen that model, you take the Kc expression, you write in the units of concentration for the appropriate number of components above the line and below the line, and then cancel out to see what units you are left with. Try the other 3 examples. Pause, try them, come back and check your answers. Okay, so let's move on to the second example. Well, the correct answer is that Kc for that equilibrium constant has no units. How do we justify that? Well, if I look at just using the square bracket for the concentration term, concentration times concentration on top divided by concentration times concentration on the bottom. So those all cancel out, so we have got no units for Kc. So as you can see already that the units for Kc are dependent on the equilibrium expression. We've got different units in the first 2 examples because we have different Kc expressions. Moving on to the next one. moles to the minus 1 dm cubed. So this is similar to previous example. We've got concentration squared on top, concentration cubed on the bottom, cancel out above the line and below the line, leaves us with 1 over moles per dm cubed, which translates to our moles to the minus 1 dm cubed. So 1 over moles is written as moles to the minus 1. 1 over dm to the minus 3 is written as dm to the power of 3. Now, if you've been unsure about those, pause and make sure that you get the last one correct. Okay, so I'm going to reveal the last one. So the units are moles to the minus 2 times dm to the power of 6. Achieved by writing out concentration squared on top, that's moles to the decimeter cubed per decimeter cubed on top. And then we've got concentration to the power of 4 on the bottom. So if we cancel, we're left with 1 over moles squared times decimeters to the minus 6. Bring those to the top line, we end up with moles to the minus 2 dm decimeters to the power of 6. Calculating Kc from equilibrium concentrations. So let's calculate some Kc values. A typical set of information would be a mixture of hydrogen and nitrogen and ammonia reach equilibrium at a certain temperature. So there is our equilibrium equation, nitrogen, 3 hydrogens, 2 ammonias. And these are the concentrations that were determined at equilibrium. 0.92 moles per decimeter cubed nitrogen, 0.76 hydrogen, 0.16 ammonia. We need a Kc expression, which follows the equilibrium law. Right hand side divided by the left hand side. Put in the values, make sure that you've got the right values for the right concentration terms, and solve. 0.0634. So there is our model. The same equilibrium at the same temperature but with different initial concentrations was allowed to reach equilibrium. The equilibrium concentrations were found to be this set of concentrations here. Can you, using these concentrations, solve for the equilibrium constant Kc? Pause, come back to check your answer when you're ready. Okay, so same Kc expression. Substitute in the correct values. Ammonia 0.21, nitrogen 0.4, hydrogen 1.2 cubed, and solve. So you've got a value that is very close to the previous Kc value. So there will be some variation due to experimental data's variation, but we can see here from this experimental data that the Kc value is maintained for different initial concentrations. So I'd like you to attempt this problem. Consider this reaction: nitrogen, oxygen, nitric oxide. Here are some equilibrium concentrations. Could you solve for Kc, that is, produce a value for the equilibrium constant Kc? Pause, come back when you are ready to check. Okay, I'm going to reveal. So there is my Kc expression, applying the equilibrium law, putting in the values that are supplied with. solving 0.0709, 3 significant figures. No units. We can also calculate Kc if we are given data just about numbers of moles. So if we were told, for instance, that 1 mole of gaseous hydrogen iodide decomposes to produce 0.114 moles of iodine, all in a 2 decimeter cubed container. So here's our reaction equation. You notice it's a 2-to-1 ratio. So let's make that clear. That's 2 moles here to 1 mole here and 1 mole here. And we put in our initial data, the initial numbers of moles. We've got 1 mole of gaseous hydrogen iodide. That means we've got 0 of hydrogen and 0 of iodine. But we're also told that at equilibrium we have 0.114 moles of iodine. So the moles of iodine has increased by 0.114. So that must also be true for the hydrogen. So we can conclude that the amount of hydrogen at equilibrium, numbers of moles, is the same as the moles of iodine there. But the numbers of moles of hydrogen iodide will have come down by 2 times 0.114 to make 0.772. Just make that point crystal clear. It's a 1-to-2 ratio. 1 mole of iodine has come about by the decomposition of 2 moles of hydrogen iodide. So if we're making 0.114 moles of iodine, the amount of hydrogen iodide must have gone down by 2 times that value. So are we ready to calculate Kc? No. Kc is based on equilibrium concentration, and we've got a total volume of 2 decimeters cubed. So our concentration will be moles divided by volume. So 0.114, we're going to divide by 2, okay, to achieve that, and that's the same for all 3. So we've now got the concentration of iodine, the concentration of hydrogen, and the concentration of hydrogen iodide at equilibrium. I've divided the equilibrium moles by 2 because the total volume is 2 decimeters cubed. The volume of the container is 2 decimeters cubed. So my concentration is moles divided by volume. I now just produce the Kc expression, plug in my equilibrium moles, concentrations I should say, plug in my equilibrium concentrations, and then solve for the value of Kc. Now there is a shortcut in this particular example whereby we could notice that the volume is the same for all of the components, and therefore where there are no units you can ignore volume, but I would advise, certainly when you're starting, that you go through the process of from initial moles to equilibrium concentration. That will avoid any mistakes. Get your equilibrium concentration values, put them into the correct Kc according to the equilibrium law, and solve for the value of Kc. In this case, Kc has no units. So attempt this problem. Calculate Kc given that 2 moles of substance A were mixed with 3 moles of B, all in a 2 decimeter cube container at temperature T. The equilibrium mixture, including the product C, was found to contain 1.5 moles of B. So our equation, something like this: A plus B, equilibrium or reversible reaction sign C. So it's a 1:1:1 ratio in this case, according to that equation. Solve for Kc. Think it through. Come back when you are ready to look at my answer. Okay, so I'm going to reveal the first few ideas. We want the initial numbers of moles. Well, we're told that we've got 2 moles of A and we've got 3 moles of B. We assume we weren't told anything different, so we have 0 moles of C, but we want to know what is the case at equilibrium. Well, we are told that there's 1.5 moles of B. So B has come down by 1.5. That means C must have increased by 1.5. If B goes down, C must go up. It's the product of the reaction of B. And it's a 1:1 ratio. And A must also have gone down by 1.5. It's a 1:1 ratio between A and B. So those are our equilibrium numbers of moles, but what else do we need to do? We need to convert those into concentrations, which we're going to achieve by dividing by 2. Divide the numbers of moles by 2 because, as in my previous example, the container is 2 decimeters in volume, 2 decimeters cubed in volume. And now we need a Kc expression, and we need to put in the equilibrium concentrations. And solve both for numerical value of Kc but also its units. Calculating Kc from equilibrium concentrations. Kc also tells us something about the position of equilibrium, or the value of Kc tells us something about the position of equilibrium. So let's look at sulfur dioxide and oxygen forming sulfur trioxide. Using the equilibrium law gives this Kc expression. Now, in its simplest form, we can think of the Kc expression as simply being a comparison between the right-hand side and the left-hand side. So the larger the right-hand side compared to the left-hand side, then the greater the value of Kc. If the right-hand side concentrations are small or low, and the left-hand side concentrations are high, then the value of Kc will be small. So if I present you with these options, could you link the value and the position of equilibrium together in the correct pairs? Pause and come back when you have done so. Okay, so if Kc is high, if Kc has a high value, that means the right-hand side value is large compared to the left-hand side. So the equilibrium position would be to the right. Similarly, if the equilibrium position is to the right, then Kc is high. Obviously, it follows, therefore, that if Kc is low, the equilibrium position lies to the left. So if Kc is low, that means these concentrations are high compared to the right-hand side concentrations. So this number would be large, this number would be small to give you a low value for Kc. So the equilibrium would lie to the left. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.